Hi, math enthusiast. I would like to invite you to join us and be a member of e-DEOlogy community. If you become a member, you will help e-DEOlogy YouTube channel to make more math videos and to ease logistics expenses. See you all in e-DEOlogy community and get this beautiful e-DEOlogy fun badge and be a member according to your interest as a bronze member, a silver member, or a gold member. We love to see you in e-DEOlogy community. Hi everyone. In this video, we are going to study basic concepts of probability. Let us define probability. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. An experiment is a planned operation carried out under controlled conditions. Random experiment is an act whose outcome cannot be predicted with certainty. For example, tossing of a coin is a random experiment. Though we know that the outcome of the experiment will result either head up or tail up, we cannot certain what it will be. Other examples of random experiments are rolling a dice and football game. A result of an experiment is called an outcome. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if the experiment is to flip one fair coin, event A might be getting at most one head. The probability of an event A is written P of A. Another example, in the random experiment of rolling a die, coming of 1 is an event. Coming of 2 is the other event. And coming of even number is another event. The first two events are called simple events because they correspond to only single outcome. Coming of an even number is called a compound event because it corresponds to more than one outcome of the experiment, namely 2, 4, and 6. We can combine events to form new events using the various set operation. The first one is A, U, B, and this is read as A union B. A union B is the event that occurs if and only if A occurs or B occurs or both. This is sometimes called OR event. For example, let event A whose outcomes are 1, 2, 3, 4, and 5. And event B whose outcomes are 4, 5, 6, 7, and 8. A union B equals 1, 2, 3, 4, 5, 6, 7, and 8. Notice that 4 and 5 are not listed twice. The second operation is A inverted U B. This is read as A intersect B. A intersect B is the event that occurs if and only if A occurs and B occurs. Sometimes this is called AND event. For example, let A be an event whose outcomes are 1, 2, 3, 4, and 5. And event B whose outcomes are 4, 5, 6, 7, and 8. A intersect B equals 4 and 5. And these are the outcomes that are common to event A and event B. The third is A complement, and we read this as complement of A. This is the event that occurs if and only if A does not occur. Sometimes this is denoted by A apostrophe and read as A prime. For example, let S be an event whose outcomes are 1, 2, 3, 4, 5, and 6. And let A be a subset of this set S, and the elements of event A are 1, 2, 3, and 4. A complement is an event whose elements are 5 and 6. This A complement has elements of set S that are not element of set A. The sample space of an experiment is the set of all possible outcomes and is denoted by S. Examples: number 1, in tossing a fair coin, the sample space is S equals H and T, where H equals head and T equals tail are the outcomes. Example 2, in tossing two fair coins, the sample space is S equals HH, HT, TH, and TT. Example 3, in rolling a die, the sample space is S equals 1, 2, 3, 4, 5, and 6. In throwing two dice, the sample space is given here. The sample space starts with 1, 1 and ends up into 6, 6. Example 5, in a pack of cards, there are 4 suits, which are hearts, clubs, diamonds, and spades, and 13 cards for each suit, that is, from ace through king. There are 52 outcomes in the sample space. Each element of sample space is called sample point. Example, in rolling a die, sample space S equals 1, 2, 3, 4, 5, and 6. Number 4, that is the number 4, is a sample point. Let us define equally likely experiment. Equally likely means that each outcome of an experiment occurs with equal probability. Example, if you toss a fair coin, a head and a tail are equally likely to occur. Let us define mutually exclusive events. A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes. Example, let event A has elements small a, small b, and small c. Let event B, whose outcomes are 2, 4, and 6. We say that A and B are mutually exclusive events such that A intersect B equals 0. Today we're going to study classical definition of probability. The probability of happening of an event E is defined as the ratio of the number of outcomes favorable to the event E to the total number of outcomes. In symbol, this is P of E equals the fraction whose numerator is number of favorable outcomes over the denominator total number of outcomes, or we say sample space. In symbol, this is equal to the number of outcomes for E over the number of the sample space. Let us have example 1. A die is rolled once. Write the sample space and find the probability of letter A. Number 3 is shown up. Letter B, getting an odd number. Letter C, getting a number greater than 4. Letter D, getting prime number. We have a picture of a die on top of our screen. In rolling a die, the sample space is S equals, the elements are 1, 2, 3, 4, 5, and 6. And then, let us write our formula. The probability of event E equals the number of favorable outcomes all over the total number of outcomes. Let's begin with problem A, that the number 3 is shown up, and we write P of 3. In our sample space, we can see that there is only one element of 3. So we write here 1 all over the total number of outcomes is 6. So the answer here is 1 over 6. And this answer we will write opposite problem A. Let us go now to problem B. The probability of getting an odd number. So we write P of odd. In our sample space, we can see that there are 3 odd numbers, namely 1, 3, and 5. So we write here 3 in the numerator over 6 as the total number of outcomes. And this 3 over 6 can be simplified into 1/2. So our answer for the probability of getting an odd number is 1/2. Let us copy this answer opposite letter B. Then let us proceed to letter C. The probability of getting a number greater than 4. So we write here P of greater than 4. In our sample space, there are 2 numbers that are greater than 4, namely 5 and 6. So we write here 2 over 6. And then to simplify, this is equal now to 1 over 3. And this answer we will write opposite letter C. There we go. Then let us proceed with problem D. The probability of getting prime number. So we write P of prime. In our sample space, there are 3 prime numbers, namely 2, 3, and 5. Remember, prime numbers are numbers greater than 1 whose factors are 1 and itself. In our solution, we write 3 in the numerator over 6. And when we simplify, this is equal to 1 over 2. Let us copy this answer opposite letter D. There we go. So we are done with our example 1. Let us go to example 2. A jar contains 3 red marbles, 7 green marbles, and 10 white marbles. If a marble is drawn from the jar at random, what is the probability that this marble is letter A, white, letter B, red, letter C, blue? Step 1, let us compute for the sample space. So we add 3 for the red marbles plus 7 for the green marbles plus 10 for the white marbles. And this is equal to 20. And then let us write our formula, and it is now written here. Let us begin with our first problem to get the probability of white. And this is equal to, in the numerator, we write 10 because there are 10 white marbles over the total number of outcomes, which is 20. So this is 10 over 20. And the simplest form is 1 over 2. This is our answer. Let us copy this opposite problem A. Let us proceed with problem B to get the probability of getting a red marble. So we write P of red. This is equal to 3 because there are 3 red marbles all over the total number of outcomes, which is 20. And this 3 over 20 is already in simplest form. So we will just copy this opposite letter B. Let us proceed now with problem C. What is the probability of getting a blue marble? Getting a blue, this is P of blue, equals 0 because there is no blue marble in the jar as given in the problem. So this is 0 over 20 and simplified into 0. It means it is impossible to get the blue marble inside the jar. So we are done with our example 2 and this is our final answer. Let's proceed with example 3. In a deck of cards, find the probability of getting a letter A, queen, letter B, diamond card, letter C, black card. In our sample space, there are 52 cards in a deck of cards. Our formula is given, and let us proceed now with our problem A. To get the probability of getting a queen. In a deck of cards, there are 4 queens. So we write here 4 over the total number of outcomes, which is 52. So this is 4 over 52. Then to simplify, this is equal now to 1 over 13. This answer we will write opposite letter A. Then let us proceed with problem B. Finding the probability of getting a diamond card. So we write P of diamond card, and this is equal to, in the numerator we write 13 because there are 13 diamond cards in the deck of cards. So this is 13 over 52. And when we simplify, this is equal now to 1 over 4. This answer we will write opposite letter B. And then let us now proceed with letter C. Finding the probability of getting a black card. So we write P of black card. This is equal to 26. When we say black card, it means the group of clubs and the group of spades combined. So that is 13 plus 13. So in the numerator we write 26 all over the total number of outcomes, which is 52. And then let us simplify this, reduce to lowest term, and this is equal to 1 over 2. And this answer we will copy opposite letter C. We are done with our example 3, and this is our final answer. Today we're going to study probability using 3 diagrams. First, let us define tree diagram. A tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. Let us have an example. In an urn, there are 11 balls. 3 balls are red, denoted by R, and 8 balls are blue, denoted by B. Draw 2 balls, one at a time with replacement. With replacement means that you put the first ball back in the urn before you select the second ball. The tree diagram using frequencies that show all the possible outcomes follows. This is an example of a tree diagram. In this level is considered to be the first draw, where there are two branches. The first branch represents the 8 balls. The second branch represents 3 red balls. On the next level is the second draw. Please note also that the problem says that the first ball is being replaced in the urn. That's why you see here there are 2 branches here under the blue balls. In this first branch there are 8 balls. In the second branch there are 3 balls. On the second group of branches under 3 red balls, this first branch here represents the 8 balls. The second branch represents the 3 red balls. Now, regarding the number here, this is 64 BB. This means the 64 comes from the product of this 8 and that 8. And this BB means the first draw is a blue ball and the second draw is also a blue ball. Here we can see 24 BR. The 24 comes from the product of these 3 and 8. And this BR means the first draw is a blue ball and the R is red ball. Here we have 24 RB. The 24 comes from the product of 8 and 3. And this RB means the first draw is a red ball and the second draw is a blue ball. In here we can see 9 RR, and this 9 comes from the product of 3 and 3. The RR means the first R comes from the red ball in the first draw and another R for the red ball in the second draw. Now, if you write the total of this 64, this 24 plus this 24 plus 9, the total will be 121, and this is the number of elements in the sample space. We can list each red ball as R1, R2, and R3, and each blue ball as B1, B2, up to B8. Now, as an example, for this 9RR, the 9RR outcomes can be written as R1, 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 R2, R1, R3, R2, R1, R2, 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 R3, R3, R1, R3, R2, and R3, R3. Let's go now to probability using tree diagrams. Let us have an illustrative example. An urn has 3 red marbles and 8 blue marbles in it. Draw 2 marbles, one at a time, this time without replacement, from the urn. Without replacement means that you do not put the first ball back before you select the second marble. Here is the example of our tree diagram. We can see here that the branches are labeled with probabilities. This first level is the first draw of marble. The first branch here represents the probability of taking a blue marble. We can see here this is 8 over 11. There are 8 blue marbles in the urn and a total of 11 marbles in it. The second branch represents the probability of taking a red marble. There are 3 red marbles in the urn, so this is 3 over 11. Again, that 11 is the total marbles in the urn. This second level here is for the second draw. There are 2 groups of branches. This first group represents the probabilities when the first draw is taking a blue marble. So here we can see that the first branch represents the probability of taking another blue marble. We can see here that this is 7 over 10. Remember, in the problem it says we are not replacing back the first marble once we get the first draw. It means there is an assumption that the first marble is blue, so there will be only 7 left in the blue marbles. So this is 7 over 10. Also, before the total is 11, since we are not returning that first marble, so 11 minus 1 becomes 10. So this is 7 over 10. The second branch here represents the probability of taking a red marble. There are 3 red marbles over 10. The second group of branches represent when the first draw is a red marble. So this branch here represents the probability of taking a blue marble in the second draw. And that is, we have 8 blue marbles over 10. The second branch represents the probability of taking another red marble. So from 3 marbles total, we assume that the red marble is already taken, so that is 3 minus 1 is 2 over 10. The numbers at the ends of the branches are calculated by multiplying the numbers on the 2 corresponding branches. Here is one probability, 56 over 110, and this represents BB. This BB means the first marble is a blue one and the second marble is also blue. The 56 over 110 is the product of 7 over 10 and 8 over 11. So we have 7 times 8 is 56, and then 10 times 11 is 110. The second probability here is 24 over 110. And this is BR. This is the probability when we have B means blue in the first draw and R in the second draw, or R means red marble in the second draw. Also, this 24 over 110 is the product of this 3 over 10 and 8 over 11. So that is 8 times 3 is 24 and 11 times 10 is 110. Another probability is 24 over 110 for RB. RB means the first marble is red, the second marble is blue. 24 over 110 comes from the product of this 8 over 10 times 3 over 11. That is 3 times 8 is 24 and 10 times 11 is 110. Last is 6 over 110 corresponding to RR. It means the first marble is red and the second marble is also red. The 6 over 110 comes from the product of 2 over 10 times 3 over 11. When we take the total of the probabilities down here, we will have this 56 over 110 plus 24 over 110 plus 24 over 110 plus 6 over 110. We can see that we have like fractions and the common denominator is 110. So we can simply add the numerators and this is equal to 110 over 110 and that is equal to 1. We can see now that the probability of drawing 2 marbles, of course this is without replacement, such that letter A, both are blue, is 56 over 110. It comes from this fraction here. Letter B, when the first marble is blue while the second marble is red, the probability is 24 over 110. Letter C, the first marble is red while the second marble is blue, the probability is 24 over 110. Letter D, when both are red marbles, the probability is 6 over 110. So this is our final answer. Let us have another example. 2 coins are tossed together. Find the following probabilities using a tree diagram. Letter A, probability of getting 2 heads. Letter B, probability of getting at least 1 head. Letter C, probability of getting at most 1 head. Letter D, probability of getting exactly 1 head. Let us write our tree diagram. Let's begin with the first coin. In the first coin, there are 2 sample spaces, and these are head and tail. The probability of getting a head is 1/2. The probability of getting a tail is also 1/2. Now, in the second coin, there are 2 possibilities also. The first possibility, when the second coin turns head, and that probability is 1/2. The second coin may be tail also, with a probability of 1/2. Now, for the second group of branches, where the first coin is turned tail, for the second coin, there are two possibilities. It may turn head or tail. For the head, the probability is 1/2. For tail, it is also 1/2. Now, let us multiply the probabilities. So, turning head in the first coin and turning head in the second coin, that is 1/2 times 1/2. And the answer is 1/4. Now, here, when the first coin is head and the second coin is tail, the probability will be 1/2 times 1/2, and the answer is 1/4. The next is when the first coin is tail and the second coin is head, the probability is 1/2 times 1/2, and the answer is 1/4. And the last, when the first coin is tail and the second coin is tail, the probability is 1/2 times 1/2, and that is 1/4. Now, using these probabilities, let us now answer letter A, probability of getting 2 heads. So we will write P of 2 heads, and this is equal to 1/4. This is the answer. Now let's answer letter B, probability of getting at least 1 head. Getting at least 1 head means it can be 1 head or 2 heads. And this is equal to 1/4 coming from 2 heads plus 1/4 when there is 1 head and a tail in the second coin, plus 1/4 when the first coin is tail and the second coin is head. So we can see here 1/4 plus 1/4 plus 1/4. And the answer is 3/4. Let us go to letter C, probability of getting at most 1 head. This means the probability of getting 0 head or 1 head. This is equal to 1/4. It comes from when we have head in the first coin and tail in the second coin. Another 1/4 comes when we have tail in the first coin and head in the second coin, plus 1/4, and this comes from tail in the first coin and tail in the second coin. So we have the answer as 3/4. Letter D, let's take the probability of getting exactly 1 head. And this answer will come from 1/4. This 1/4 comes from when we have head in the first coin and tail in the second coin, plus another 1/4, and this comes from tail in the first coin and head in the second coin. So we have 1/4 plus 1/4 equals 2/4, and this 2/4 can be simplified into 1/2. So we are able to give the answers in all our problems in example 2. Today we're going to study empirical probability. Let us define empirical probability. Empirical probability uses the number of occurrences of a given outcome within a sample set as a basis for determining the probability of that outcome occurring again. The empirical probability that an event A will occur is given by this formula. P of A equals number of times event A occurs all over total number of trials. Let us see example 1. You flipped a coin 100 times. It was recorded that 53 heads turned up. What is the empirical probability of getting a head? For our solution, let us write our formula. P of A equals number of times head occurs all over total number of trials. So our answer is 53 over 100. This is the final answer. Example 2. A class has 25 students. One student is absent today. If 19 students turned in their homework today, what is the empirical probability that the absent student will submit his homework when he returns? For our solution, let us write our formula. This is equal to number of students who submitted homework all over total number of students present on that day. This is equal to there are 19 students who submitted their homework all over there are 24 students present on that day. So our answer 19 over 24. This is the final answer. I hope you learned something from this video. See you again next time.